Right, so we'll finish up this week by looking at the last half of section 8.1. Okay, so just as a reminder of what the law of sines is, sine of alpha over A equals sine beta over B equals sine gamma over C. Sometimes you see it flipped. So in some textbooks, you might see A over sine alpha equals B over sine beta equals C over sine gamma. And it's the same thing. So this is the first law. The next law we're going to learn in section 8.2 is the law of cosines. And between law of sines and cosines, you can solve every kind of problem you would need to about sides and angles in a triangle. There's also a law of tangents. I'm not really familiar with it. I'd have to look it up and see what it is. It might be a totally separate kind of topic, but we don't study the law of tangents in this class at all. I'm not even sure it's in your book, but it does exist. Okay, so as far as notes, there's really nothing new I need to describe as like for process on how to do it. You know everything from yesterday, so we'll just try to solve it and see what happens. Okay, so when we have a problem like this, what's the first thing that we usually want to do before we even do any calculations? Okay, before we even decide that. Yeah, we're going to draw it out and see what kind of triangle it is. And then from there, we can decide, should we be using law of sines or law of cosines? Obviously, you don't know law of cosines yet, so you probably know what's going to happen. Remember, my triangles are never drawn to scale. That's purely just so I get the relationships of what's across from what correct. So I'm going to put A, alpha. I'll put B, beta, C, gamma. Okay, looking at the triangle, how would you classify that triangle using the three letters, A's and S's? Yep.
Side, side, angle.
Yep, you know a side, and an angle. And the key that tells you this is law of sines is that the angle that you know is not between the two sides. You don't know gamma. If you knew gamma, you wouldn't be able to use law of sines. Because if you knew gamma and alpha was unknown, then you'd know one piece of information in each row. That's not, can't work that way for law of sines. Okay, law of sines is going to have a full row. Okay. Also, is this the kind of problem where you could find any one of those boxes first, or do you have to find things in a certain order? What do you think, Sam?
You have to find the angles first.
Yes, you have to find things in a certain order. Can you be more specific about which angle you have to find first?
Beta.
Yes, you have to find beta. Then you can find gamma. Then you can finish up with finding C. You have to follow that order. Okay, so let's set it up to find beta. So Shauna, could you set up my proportion for me to find beta?
So you would 35 over 6 equals sine beta over.
Hey, what did you say? Sine of beta? Yep. Anything else? Maybe if I didn't hear it or you didn't say it, I'm not sure. Not sure. Anybody tell me what I'm missing there? Yep.
Sine 35.
Yeah, I wasn't sure if you said 35 over 6 or you did say sine. I wasn't sure. So now we've got everything set up. We're going to cross multiply. Actually, you know what? You don't even need to cross multiply. Just multiply both sides by what number? Yeah. Yeah, just multiply both sides by 8. So you get 8 sine 35 divided by 6 equals sine beta. But we want beta. Sam, how do I get rid of sine?
Reverse sine, or arc sine.
Arc sine, yep. So arc sine or inverse sine and we're going to take the inverse sine of each side. So do it on the left, do it on the right. Now, on the right, inverse sine and regular sine cancel because there's nothing else there. They don't cancel on the left. All you can do is type all that in the way it is. Because you have the 8 and the 6, it messes up canceling the sign. Okay, so just type it in exactly the way you see it. Yes, you can reduce 8 and 6, but if you're just typing it into the calculator, what's the difference if you press an 8 and a 6 or a 4 and a 3? Doesn't save you any time. So I would just leave it. All right, so we've got, first thing I'm going to do is put it in degrees. And we're going to do second inverse sine of 8 sine 35, close parenthesis, divided by 6, close parenthesis. Okay, so I get an answer of 49.886. So this is not a no solution problem. How do I know? I just got a solution, 49.886. Okay, so I have at least one solution. Before we continue, for these kinds of problems, and also what we did in 7.5 and 7.6, you're not going to need a graphing calculator to do any of it, especially in 7.6, because that's solving equations. We've already solved them graphically, so I want to make sure you know how to solve them algebraically the way we did this week. So for the test tomorrow, we're going to stick with just a scientific calculator. Does anybody want to borrow one now to practice typing that in? It's exactly the same. There's no difference between how you type it in on a graphing calculator and my scientific ones. There's no difference at all. But does anybody want one just to try it? People know the kind of graphing calculator I'm talking about, the blue ones. Is that, yeah, exactly like that. Yep. So you can use your graphing one today, but I just want you to be familiar with the scientific one, just in case. But you probably used them in geometry last year in Algebra 1. So just make sure you get 49.886. After this test, I think most other tests you can use graphing calculators, and that's fine. But I just want to make sure you can do the algebra stuff. All right, so beta 1. I'm calling it beta 1 just in case there's a second answer. Okay? If there isn't, then don't worry about it. We'll just do this like we always would. What do I do with that number to check if there's a second answer?
You do 180 minus 49.86.
Yeah, so I do 180 minus 49.886, and I get 130.114. So mathematically, that's the second answer. Does that work in this triangle? Okay.
Yeah, because if you add the only known angle, which is 35, it's still below 180.
Yep, if you add the angle that you were given, 35 to 130, you get 165.114. So the other angle is small enough that it does work. Okay? So that's going to be beta 2. What was it? 130.114. So now, because we got 2 answers for beta, we are going to have 2 answers for gamma, and we're going to have 2 answers for C. You don't get 2 answers for the given stuff. What was given is given, that's just the way it is. There's only 2 answers for what you have to find. And if you're wondering, well, what sides and what angles are in the 2 different triangles? Alpha is going to be, we'll call it the red triangle. Beta 1 is going to be in the red triangle, and gamma 1 is going to be in the red triangle. For the other triangle, it's going to have alpha, so alpha is in both, beta 2, and gamma 2. So those are the 3 angles that are in the green triangle. Okay? As far as the sides, it's kind of the same idea. Alpha is in the red, B is in the red, C1 is in the red. There are the 6 things in the red triangle. For green, A, B, C2. Those are the 3 sides in the green triangle. So we're really solving 2 problems at the same time. We're just using the same table. So to find gamma 1, take all the angles in the red triangle, add them up, and then subtract from 180. So we got 180 minus 35 is in the red triangle, minus 49.886. So I get 95.114. And now we're going to use the 95 to find C1. We're going to use gamma 2 to find C2. So let's get gamma 2 first. How would I get gamma 2?
Add the green triangle angles, so 35 and 130.
Yep. So 35 and 130.114, so that's 165.114. And subtract that from 180. Okay, so that leaves 14.886 for gamma 2. Okay, now we're almost done. Last thing we need to do is find C1 and C2. Now, like we've done before, I have some choices. I have 2 rows. Let's start with the red triangle, C1. Okay, I have 2 red rows that are complete. A, alpha, that's a complete row in the red triangle. B, beta 1, that's another complete row. Which row should I use? Yep.
Alpha because it was given.
Yeah, we're going to use the row with alpha. Okay, so let's find C1. And we're going to set it up exactly the same way we started when we found beta. Sine 35 over 6. Okay, in fact, when we find C2, we're going to also set it up the same way, because A and alpha is also in the green triangle. So we can use that row again. And again, it's good because it was given. So sine 35 over 6. Okay, so now let's set it up for C1. What would go on the other side, just sign up for me. What would go on the other side of that proportion to find C1? Sine of what over what? Yep.
Sine of 95.114 over C1.
Yep. So sine 95.114 over C1. And while we're setting it up, can somebody set it up for C2 for me? Yep.
It would be sine 14.886 over C2.
Sine 14.886 over C2. And now we're going to solve each one. Okay, so when I solve for C1, Jan, what's C1 going to be after I cross multiply and then isolate C1?
It would be so it would be 6 sine of 95.4 divided by sine 35.
Yep. So we'll type that in. Good. See what we get. C2, you're going to set it up exactly the same, except instead of 95.114, put 14.886. Everything else stays for numbers stays the same. So we have 6 sine 14.886 over sine 35. Okay, now we just need to type those in. Yes?
Did you originally put parentheses around that?
Um,
Or is that just how you wrote it?
No, I just wrote it that way. I thought about that as I was doing it, but no, you don't need parentheses really. When you would need parentheses if you were going to have something else after it. The other thing is when you type it on the calculator, it is going to put the parentheses. So in my head I was like, oh, I'll make this look like it would on the calculator. But yeah, you don't need it. So let's start with C1. Does anyone have the decimal for that? We'll go to 3 decimal places.
Oh, I only went to 2.
You went to 2?
Yeah, I got 10.42.
10 point, okay, did anyone have it to 3? Because then we can double check. 10 point,
It's 0.419.
okay, perfect. And since you both got the same thing, chances are we're on track. And then how about C2? Leo?
2.687.
687. Okay, thank you. Okay, so let's just check the red triangle. The biggest side is C1. Biggest angle should be gamma 1. Yep. Smallest side is A. Smallest angle for the red should be alpha, and it is. Let's look at the green one. Biggest side for the green one is B. Biggest angle should be beta 2. Yep. So everything looks reasonable. Okay, so that's the longest kind of problem you can have with law of sines. It's called the two-solution case or the ambiguous case. Sometimes you see that in the textbook. Okay. Any questions on that? All right, so let's sketch that. So if I gave you guys like this exact information, I said, here's a piece of wood that's 6 inches long, here's another piece of wood that's 8 inches long, here's a protractor, I want you to measure angle alpha, make it 35 degrees, and here's some other pieces of material, make a triangle. Some of you might make the red triangle, some of you might make the green triangle, just by putting pieces together. So we're going to look at how that could happen. So I'm going to start with this triangle. Okay. And what I'm going to do first is just make a copy of that side. Now, by doing that, does everybody agree that that side is the same as that side? Okay, so those are the same. I'm going to take, and there's different ways to do this, but I'm going to take this side, I'm going to make a copy of it, and I'm going to flip it. And I'm going to put it right there. Does everybody still agree that that side and that side are the same length? All I did was a mirror image, so that doesn't change the length. Okay, and for the third side, I'm going to connect the bottom. And now if you're like, well, wait, what's the angle that's the same? Well, look at this. That angle in the lower left is exactly the same in each triangle. So what I just did is created a side-side angle, 2 different versions. That's the case we just solved. You can't do that with any other case. Like if you gave me a protractor and some sticks or whatever, and you gave me an angle, and a side, you would all draw exactly the same triangle. There are not 2 different versions. If I gave you a side length, and a side length, it's one we haven't done yet, but you would all draw the same triangle. Okay. This is the only case that this can happen. Side-side angle. Any questions on that? All right, so let's look at another one. Okay, first of all, just by looking at it, I can tell that it's the case where we have to be careful because you have a row with everything in it and you have a row with nothing in it, and you have no way to find anything in that row. So this is the kind of problem you're going to have to find things in a certain order. Okay, what do you have to find first here? The alpha. You've got to find alpha. So let's set it up. And Caleb, can you set that up for me?
Sine of 50 over 1 equals sine of alpha over 2.
Sine of alpha over 2. And you really don't even need to cross multiply. All you need to do is multiply each side by 2. And because the denominator on the left is a 1, you don't even really need it. So it's just going to end up being 2 sine 50 equals sine alpha. Now, before I go any further, does anybody remember as a decimal what the sine of 45 is? And I'm just thinking 45 because that's one we should know, and it's kind of close to 50. What's the sign? It's one of those special decimals that comes up. It's the square root of 2 over 2, but you want to remember what that was? Yeah?
45.
Well, that's the number you would plug in to get the decimal I'm thinking of. So when you put in 45 and then press sign, you hit enter, the decimal that you get is
0.707.
it's 0.707. Well, if I know that, think about your graph of sine for a second. Okay, 40, this is 90, right there. Okay, that's where you hit the highest point. So from 0 to 90, the sine function is going up. And it's getting closer and closer to what number? 1. So if the sine of 45 is 0.707, the sine of 50 is a little bigger. Okay, maybe it's 0.75. If you double a number that's 0.7, what do you get if you double 0.7? Because that's what this is saying to do. Yep. You get 1.4, or in this case, something a little bigger than 1.4, maybe 1.5. So you have the sine equal to 1.5. What's going to happen there? The sine function equals 1.5. That's a no solution. Okay? If you didn't remember what the sine of 45 was, you can type this in, and we get 1.53. So now what you'd be trying to do is taking the inverse sine of 1.53. You can't do that. Okay? That's a no solution. If you're still not sure, try it. Take inverse sine of each side on your calculator. You just bring the calculator up. Just bring it right up. Second, inverse sine of 2 sine 50. Error. Okay? It says it can't do it. Alright, so if you realize that early on though, then you don't even have to waste time plugging it in and then be like, oh geez, did I do something wrong? No, you didn't do anything wrong. It's just this is a no solution. Okay, so that means you can't find alpha. So if you can't find alpha, then you can't find
Anything else?
You can't find anything. Because now that you have alpha, what you would normally do is add that up, add it to gamma, subtract from 180, and you'd get beta. But you can't do that. And if you can't get beta, you can't get the side that's across from it. Okay, so very nice in terms of work, because you really do one calculation, and then you're done. So this is a no solution problem.
Will we always find no solution on the first step we do in no solution problems?
Yep. Yep. Because no matter what you solve for, which you have to solve for this, you have no option. Even if you could solve for something else, it would also be no solution. But you can't. You have to do alpha first anyway. Yep. Okay, so I'm going to try to sketch that and see what happens. Before I do it, what do you think is going to happen if I try to draw this triangle? I'm going to use a protractor and I'm going to measure things perfectly to scale. What do you think is going to happen? Leo?
2 of the sides will intersect.
Yeah, it's not going to be a triangle. Right? 2 of the sides probably aren't going to reach, or maybe one of the sides is going to be too long. Let's see what happens. All right, so I needed to measure an angle of 50. I already used a protractor earlier, and that's exactly a 50-degree angle. Okay, I measured it, it's 50. But I need a side that's 1 unit long and 2 units long. I don't really have to measure that and use like inches or anything like that. I can just say that's 1 unit long, and then create something twice as long. And that's now 2 units long. So 1 unit, 2 units. Any questions on that? Okay, but what I need to be able to do is rotate. Actually, can I rotate that? Let's see. Yep, so now I can rotate that if I need to. This one, I can't rotate it, so it's kind of weird. I have to group it with something. And then I can erase what I grouped it with. And now I can rotate it. I figured that out one day. All right, so A is 2 and C is 1. So what I'm going to do is I'm going to set A at exactly a 50-degree angle. So let's see if I can just line it up. No, close enough. It's just about at a 50-degree angle. So there's A. I cannot change that. I can't change the length of it. I can't change the angle of it. I have to keep it at a 50-degree angle to the horizontal. B, I don't know. C is the side that comes off up here. Okay, so that's C. B, you don't know. You can make B as long or as short as you want. So there's B. It can be any length you want. Also, this angle at the top is unknown. You can make that angle anything you want. You can turn it, reposition it. But no matter how long or short you make B, or what angle you put that short side at, is it ever going to reach the bottom? No, it's not long enough. So it's a no solution. So kind of an interesting question would be, well, how long would you have to make that side? What would be the minimum length you could make that side and have a solution? How, what's the shortest possible number to make it work? Obviously, if you make it long enough, at some point, you could just stretch it down and it would reach. No matter what angle you really put it at, as long as you don't go beyond parallel to the bottom side. So even if you put it like that, you could extend it at some point and reach. But my question would be, what would be the shortest you could make it and have it reach? So if you think about that, you can figure it out. But for now, that's not really what we're going to look at. Okay. So any questions on why that's a no solution? All right. Okay, so let's look at a word problem. So the word problem, a couple things. One, there's a lot of information that we have to turn into a picture. And two, they're going to use compass headings. So normally when we label stuff, we put 0, 90, 180, and 270. Well, on a compass, they use the directions instead. So we have north, south, east, and west. So the way they're going to give us a bearing is they might say off in a direction 10 degrees east of north. So what that means is if you were going straight north and then you went off 10 degrees, that's a direction 10 degrees east of north. I guess you could also say it's 80 degrees north of going east. So you could say it either way. Any question on that? So that's how they're going to describe the directions of this problem. If you're familiar with compass headings, usually north is 90. North is 0, east is 90, 180 is south, 270 is west. So if you look up like a plane and you're tracking like someone's flight to see if they've landed, usually the direction of the plane is given, and if it says the plane is traveling at a heading of 270 degrees, that means they're going west, not south. So compass headings are a little different than the way we do it in math, but if you use this kind of description, 10 degrees east of north, it eliminates that confusion. So that's how we'll do it. All right, so let's look at that one first. Okay, so we have two Coast Guard stations. We're going to call them Coast Guard Station Zulu and X-Ray. And we know the distance between the two Coast Guard stations. Okay, they're 120 miles apart. And it says here that a ship sends out an SOS. And for our purposes, you don't really have to think about all the details, but pretend the ship, the GPS isn't working on the ship. It's nighttime, so they can't see any landmarks. It's cloudy, so they can't see any stars. They have no way to navigate. All right? But they have a radio, so they send out a signal. And the Coast Guard station Zulu receives the signal, and the direction they receive the signal from is at a bearing 40 degrees east of north. From the perspective of their Coast Guard station. 40 degrees east of north. Now, if you're like, well, how could they figure out the direction? Well, don't think about it as an SOS then. Think about like they have a big beam of light on top of their boat. And the Coast Guard station sees the beam of light then. Okay, so think about it that way if it doesn't make sense to you. So they see a beam of light and they say, you know what, it's coming from that way. But the problem is, if you see a beam of light, like this little dot, what don't you know? If you were standing on the beach and you saw like a dot of light, you know what direction it's coming from, you could point to it, but
You don't know the distance.
you don't know how far it is. Maybe it's 20 miles away, maybe it's 50 miles, maybe it's 100 miles. That's where somebody else needs to see the same thing you're seeing, and then you can triangulate the position. So the other station gets a signal over the radio, or they see the same beam of light, and from their perspective, it's coming at a direction 30 degrees west of north. Now that's the key. You know how far apart the Coast Guard stations are. Each Coast Guard station can see the same thing. One Coast Guard station can say, you know what, I see it coming from that direction. The other one says, I see it from another direction. They can basically calculate an intersect point. And that's where the boat would be. So what I want to figure out is how far each station is from the ship. And this kind of thing, they do actually do it. I don't know if they do it with boats. That's the problem from our book. But I have seen it done with fires in a forest. So two, ranger stations. Like if one ranger station can see smoke, they have this thing in their tower. It's like this big disc, and it's labeled with degrees. And they can spin it, and it has a sight. So they spin it, they line it up with the smoke, and they can say over the radio, I see a fire at a heading of whatever. They describe the direction they see the fire. And another tower does the same thing, maybe 100 miles away. They line up their disc, they look through a hole, they line up the smoke, they look down and they say, okay, I'm looking at an angle of 50 degrees. And then each station sees the same smoke. That's how they can pinpoint where a fire is. Because in the forest, sometimes it's just trees, so you can't really say, oh, the fire is over by the tree. Not very helpful. But that kind of works. And that would actually be simpler than this problem, because in real life, if your boat is in the ocean, it's obviously not staying still. It's moving. So if you can't get to the boat for 6 hours, the boat is going to be nowhere near where you can see it now. It's going to drift with the current if they didn't have engine power. So yeah, there's a lot of other things that can complicate it, but we're trying not to look at all that stuff. All right, so let's see if we can figure out where the boat is. So we need a picture. So the first thing we need is land. Okay, that represents where the two Coast Guard stations are. Okay, so let's just draw that in. So on this side, it's going to be land. Out there is going to be water. Okay, so we've got two Coast Guard stations. 1, 2. And how far apart are the two stations? Yeah?
120 miles.
They're 120 miles apart. And that distance would be known. They could look up the distance between these two objects because they're on land, so there's probably some record of how far apart they are. Okay, so we've got the distance between the two stations. We've got a boat out there somewhere. There's our boat. I tried not to draw it in the middle of the two stations. At this point, I don't know if it's closer to the one on the left or the one on the right. Okay, so my picture might not be this good. But it says that Coast Guard Station Zulu is 120 miles west of X-ray So Zulu is to the west of X-ray. Okay. And now we're going to kind of draw in a line of sight from each Coast Guard station to where they see the boat and where the other station sees the boat. So we've just created a triangle, but now we need to measure some angles. So the directions are indicated from a bearing of north. So what we need now is a line from the perspective of each station that represents north. Well, north is easy, just up and down. So put a line in. And if you were at this station and you looked along that solid line, you would be looking north. Okay. Do the same thing for the other Coast Guard station. Draw in a line, put it right there, and if you looked along that solid line, that would be north. North. All right, now technically, you might be looking at that and be like, well, wouldn't that mean north is in two different spots? Okay, so maybe the line should be tilted in slightly, because if everything is going towards the North Pole, the lines would be tilted in just a little bit. But that's really going to complicate our problem. So let's just pretend north is, straight up from that perspective. Okay, so the first one says, the call to Zulu comes in 40 degrees east of north. So where would I label that? From the perspective of Zulu, 40 degrees east of north. Yeah.
It'd be 40 degrees between the north line and your sight line.
Yep. So there's your 40-degree angle. Now, is that angle inside the triangle? No. But can we figure out the one inside? Sure. If the one on the outside is 40, what would be the one on the inside? Yeah. 50. Now we're getting somewhere. We have an angle, we have a side. We're going to have another angle in a second. The other one says the call to X-ray is 30 degrees west of north. So I think I put the boat in the wrong spot, so my picture's not to scale. So where would the 30-degree angle be? Jane?
In between north at X-ray and their sight line.
Yep, so 30 degrees west. West is to the left from that perspective. So that means the angle inside would be 60. So now we have angle, side, angle. We've got a triangle we can solve and find the distance to each Coast Guard station. Okay, so that's the hard part. Now the rest is just kind of stuff we've done before. All right, so we need to label these distances. And you can call them whatever you want. You can call this A and B. So now let's find A and B. So we don't have things labeled as alpha, beta, and gamma. So now you just have to know the general idea. Sine of an angle divided by what's across from it equals sine of an angle divided by what's across from it. Now, in that diagram, do I know any angle and the side that's across from it? The way it is right now.
No, but you can find it.
No, but I can find one, right? So this is like the problem where you don't have a complete row, but you can find something that would give you a complete row. What would that last angle be?
70.
Yep, would be 70, because 50 and 60 is 110. That's 70. The problem didn't ask you to find that angle, but you're not going to find what you do need without it. Now you have an angle and what's across from it. So, if I wanted to use those two pieces of information, how would I plug them into my law of sines? Sam?
Sine of 70 over 120. So sine of 60 over A.
Yep. So sine 60 over A. And let's set up B at the same time. We can come back and solve that. So sine of 70 over 120 again. Equals, now I need my other angle, sine 50 over B. Okay, so we've got our setup. So A is going to be 120 sine 60 over sine 70. And does anybody have an answer for that? And remember, this answer is in miles. Liam?
10.593 miles.
10.
Well, 110, sorry.
Oh, 110. Yeah, I was going to say this side is pretty big, so it's probably a little bigger than that. So what is it again?
110.593.
110.593 miles. For the purposes of, actually finding and rescuing people on the boat, they'd probably just say it's about 110 miles that way. They're not going to exactly measure to the nearest inch because, once you see the boat, if you're within an inch of it, you'll be okay. You'll see it. But that's great for accuracy. And then B, any question on the setup? 120 sine 50 over sine 70? Okay, does anybody have what B is? Just by looking at the angles, B should be shorter than A, a little bit. Yeah.
97.825.
97.825 miles. Any question on that one? Okay, so now a decision somebody might have to make is, all right, if we have to rescue them, which Coast Guard station could get there quicker? Well, B is closer, but it would also factor in what kind of equipment does B have? Do they only have boats and maybe A has a helicopter and they can go 3 times as fast? Is it, too windy to launch a helicopter? We got to go with a boat, things like that. But B is closer than A at this moment in time. If that boat is drifting, then, and each station says, well, I can get there in 5 hours and I can get there in 4 hours. Well, where is that boat going to be in 4 hours? Is it going to be drifting closer to one of these stations? So that would have an effect too. I actually heard a story when I was on a cruise over break, and somebody had asked the cruise director, have you ever had a man overboard? Which basically means somebody fell off the ship. And he said, yeah, we had somebody fall off once, and he was doing it for, I think, 14 years. So one person fell off the cruise ship, and he said, we didn't even go back and look for him. And people kind of laughed, because his personality, he really made people laugh. And I was like, it's kind of weird the way he said that. What he probably could have said was, the person had fallen off the boat in the middle of the night, say midnight. By the time they found out about it, it was like 6 in the morning. So by the time you're already 6 hours away, you would have to go 6 hours back. There's no way you're going to find anybody in the ocean if they've been drifting for 12 hours. They're just a small person. I mean, 12 hours, they could be hundreds of miles from where the boat was. And you're looking for a target that may be 6 feet big in the middle of the ocean. You're not going to find them. So that's why they didn't go back in and look. So that's kind of the point. You can't assume if something falls in the ocean, it's going to stay right where it is. Things drift. So these kind of problems are really much, much more complicated. Right. So any questions on that? All right. So the last one we're going to look at is this one, and it's about measuring the height of an object that's in front of you, or somewhere you can see an object. You want to know the height of it, but it's not easy to just go up and use a tape measure. Maybe it's a tree, and you want to get a good estimate for the height because you're going to cut it down, and you know the house is 70 feet away from the tree. So if the tree is less than 70 feet tall, you're pretty safe the tree's not going to hit the house, no matter which way it falls. But maybe if the tree is taller than 70 feet, you got to make sure the tree falls a certain way so then it doesn't hit the house. So you could use what I'm about to show you to find the height of anything. A mountain, as long as you can see it, and you can measure a couple things. Okay, and what you need to measure doesn't involve going up to the object you want to measure. So if there was like a canyon and you wanted to know the height of something on the other side of it, yeah, you could do it. You don't have to go up to your object and measure anything. what you need to do is take two sightings of your object. Okay, so a sighting is basically, if you had, sometimes you see like surveyors use like a tripod and they have something on top of it, and then they have like another tripod and they're looking at it. Does anyone know what I mean? Like on the side of the road. They're measuring things. They're measuring, sighting different things. Well, what we would have to do is take two sightings, and it doesn't really matter how far apart they are. It'd be better if you don't do one, say at 1 foot apart. That's kind of close. Make them 100 feet apart, 500 feet apart, 10 miles apart. It doesn't really matter, but a good distance apart. And the first sighting, okay, the person sets up their transit, they look through the top of it, they set their scope right on the top of this object, and they measure an angle of 47 degrees from their perspective to the top of this object. In our case, it's a mountain. And then they back up 900 meters, and they're going to do another sighting. So the angle is going to change this time. If you're looking at an object that's higher than you are, and you're very close to it, and then you start to back away from it, what happens to the angle you need to look at? If you keep your eyes focused on the top of whatever you're looking at, as you back away from it, what happens to your angle of elevation?
Yes.
Yeah, it decreases. Think of like a movie screen, right? If you're really close to it, you're looking up, as you start to move back from it, the angle you look at decreases. So when this person backs up 900 meters, the angle is now 35 degrees. Okay, just to keep it a little bit simpler, we're going to assume that the tripod is level with the ground. For the purposes of measuring a mountain, that means you're going to be off by about 4 or 5 feet. Because normally what you have to do is add in the height of the tripod to your calculation. Because you're not measuring things from the ground, you're measuring things from the height of the tripod. But we'll ignore that. Okay, so what do you think we need to do with all that stuff? That would make this a lot easier. Yep.
Make a picture.
Yeah, we're going to make a picture. So in the picture, we definitely want to have the ground. Okay, we have to have a mountain. Alright, so here's our mountain. It's very steep. Careful if you climb it. And the surveyor takes two sightings. We'll just say here and here. How far apart are those two sightings? Yeah?
900 meters.
900 meters. Okay, so those are 900 meters apart. And I'm going to draw in a dotted line for the two sightings. To the peak and to the peak. Now the angle of elevation, think about that if like you were firing a cannon. It's the angle that you would elevate whatever you're firing to be aimed at your object. So the angle of elevation is always with the horizon. So the first sighting, we get an angle of elevation of 47 degrees. So it's a 47 degree angle between the line of sight and the horizon. Then we move back a little bit. What was the second angle of elevation? 30 what? 35. So our goal is to find the height of the mountain. That would be that side right there. So eventually we want to be able to work with this triangle right there. And what kind of triangle is that? Yep. Yeah, it's a right triangle. So let's move that triangle down and see what kind of information we have about it. There we go. All right, just ignore that. Okay, so we know the angle in the lower left is 47. That's the height of the mountain. Do I know anything else about that red triangle? Sam?
Under the 90 degree angle.
Yeah.
Which should be the other one.
Yeah. So we know that's a 90. So yep, we could find this other angle at the top if we wanted to. Do I know anything else about side lengths? But Tessa, what do you think? Do you know any of the sides in that red triangle? No, we don't. That's a problem. If you don't know any of the sides, you're stuck. You can't use that triangle right now. Eventually we can. So we're going to have to look at another triangle first and figure out something else. Does anybody see another way that I could draw a triangle that I have more information about, or I can find information based on what's given? Yep.
The one between the two sight lines is 900 meters.
Yeah, let's make that one green. So the green triangle, we know a little bit more about. Just make a copy of that down here. We know that this angle is 35. This side is 900. And what else can I find, even though it's not labeled?
You can find the angle that's like the other angle, not the one on the top, the one on the bottom right.
Yep, we can find the one at the bottom because this angle and 47 form a linear pair, so they add up to 180. So 180 minus 47, that gives me 133. And now what else can I find? Yeah?
You can find the third angle.
Yeah, I could find the third angle. And that's important because now if you know an angle and the side across from it, law of sines is going to work for something. So we have 168. Subtract it, we get 12. And now I kind of position these so you could see something. If you look, the hypotenuse of the red triangle is this side of the green. So find that side of the green triangle, and then you'll know the hypotenuse of the red one, and then you've got the side and an angle, and you're good to go. So let's call this side A. Using law of sines, can somebody set up a proportion for me to find A? Yeah?
Sine of 12 over 900
Sine of 12 over 900. Yep.
equals sine of 35 over A.
Yep, exactly. So let's find A. Let's see what we get. So we're going to have 900 sine 35. 900 times sine of 35. And then we're going to have to divide by the sine of 12. Okay, so we get 2,482.88 meters. Is that the height of the mountain? No, it's not the height of the mountain. 2,482.88. It's the hypotenuse. Okay, I won't put meters because that'll just look confusing. So now that we know that, we can find the height. Okay. What trig function would I use, thinking SOHCAHTOA now, to get the height? Look at the angle that I know and figure out the names of the two sides. Yeah.
Sine.
I'd use sine. So the sine of 47 equals opposite over hypotenuse. And what would be my last step to get the height by itself? Well, time?
Well, I use inverse sine. Wait,
No.
no.
Yeah, we don't need inverse sine.
Multiply by the hypotenuse. So
Yeah, multiply the sine of 47 times the hypotenuse. The only time you need inverse sine is when your variable is inside the sine function or cosine function. Okay, so we get a height of 1,815 meters. Or 1,815.9. And assuming that you took your sightings accurately, that would be the height of the mountain. It all depends on how accurately can you measure your angles of elevation. You need a pretty good tool to do that with. Okay, so in terms of mountains, is that a tall mountain? Well, if you figure roughly, there's a little more, 3 feet to a yard. A meter is a little bit longer than a yard. So if you triple that, that would tell you roughly how many feet tall it is, and it's probably a little taller than that. So about 5,600 feet tall, just a little bit shorter than Mount Washington, which is the tallest mountain in the Northeast. So yeah, it's pretty tall. Mount Wachusett, just to compare, is 2,006 feet, 2,008 feet, it's right around there. So it's more than that. Mount Monadnock is 3,165, so it's taller than that too. It's a pretty good size mountain. Nothing compared to mountains out in like Colorado though. So. Okay, any questions on that? All right. Notice both of these problems did not have multiple solutions because that wouldn't make sense. It's not like you could say, well, the mountain could be this tall or it could also be this tall. No, it's just one height. Okay. Same thing here. It's like saying the boat could be here or here. Nope, the boat is only in one spot. So these kind of problems only lend themselves to one solution, not two. Okay, so homework, same section as last night. There's no extra problems from the on the board though. It's all in the book. So page 435, 4, 9, 11, 13, 14, 18, and 19. So these are going to focus mainly on two solution, no solution. Remember, I'm not after school today because I stayed yesterday, but we will go over this before the test tomorrow. And for the test tomorrow, only scientific calculators, no graphicals. Yep.
One of my teachers said we're supposed to get like 11,000 feet of snow tonight, and we're not going to have school
It's a lot of snow.
tomorrow.
It looks like it's going to be 40 tomorrow, so during the day. So it looks like it's going to be a lot of rain, but it is going to snow maybe more at night. So I'm thinking we'll be okay, but we'll see what happens.
Yeah.
If for some reason we didn't have class, then we wouldn't have a test. And
No, we wouldn't make that.
no, you'll have a lot of signs on your next test because I want you to differentiate between sines and cosines, but you would never have a test on 7.5 or 7.6.